Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Volcanoes are among the most dramatic and powerful expressions of planetary energy. On Earth, they shape continents, create new land, influence climate, and remind humanity that our planet is alive beneath our feet. Yet Earth is only one small stage in a much larger cosmic theater. Across the solar system, volcanoes erupt in forms far stranger, larger, and more extreme than anything found at home. Some spew molten rock hotter than any lava on Earth. Others spray fountains of ice and vapor into space. And some may even help sustain hidden oceans where life could exist. The story of solar system volcanoes is a story of fire beyond Earth, revealing how worlds are born, evolve, and sometimes remain active long after they should have gone cold. To understand volcanoes beyond Earth, it helps to first understand why volcanoes exist at all. At their core, volcanoes are pathways for internal heat to escape. Planets and moons are born hot. Energy from their formation, radioactive decay, tidal forces, and chemical reactions becomes trapped inside. Over time, that heat seeks release. When the conditions are right, molten or partially molten material rises, breaks through the surface, and reshapes the world above. The details depend on gravity, composition, temperature, and the presence of water or other volatile substances. Change any of these factors, and volcanoes become something entirely new. Earth's volcanoes are driven primarily by plate tectonics. Our planet's surface is broken into moving plates that collide, pull apart, and slide past one another. At these boundaries, magma forms and erupts. But Earth is unusual in this respect. Most other rocky bodies in the solar system lack active plate tectonics. Their volcanoes operate under different rules, offering scientists a natural laboratory to explore volcanism in its many forms. The moon provides the first hint that volcanic activity was once widespread beyond Earth. When we look up at the moon, we see dark, smooth regions known as maria. These are vast plains of solidified lava, formed billions of years ago when the moon was volcanically active. Lunar volcanism was gentler than many eruptions on Earth. Instead of explosive eruptions, lava flowed quietly across the surface, filling low-lying basins created by asteroid impacts. Over time, as the moon cooled and lost its internal heat, volcanic activity faded away. Today, the moon is geologically quiet, but its ancient lava plains preserve a record of a once fiery past. Mercury tells a similar yet distinct story. As the smallest and innermost planet, Mercury experiences extreme temperature swings, but beneath its battered surface lies evidence of widespread volcanism. Spacecraft observations have revealed enormous lava plains and volcanic vents scattered across the planet. Mercury's volcanism likely occurred early in its history, when the planet still retained enough internal heat to melt rock. Unlike Earth, Mercury has no atmosphere to erode or hide its volcanic features, so they remain frozen in time, offering clues to how small rocky planets cool and evolve. Venus, often called Earth's twin, may be the most volcanically intriguing planet of all. Similar in size and composition to Earth, Venus is shrouded in thick clouds and crushed by immense atmospheric pressure. For decades, scientists debated whether Venus is still volcanically active today. Its surface is covered with vast lava plains, towering volcanic structures, and features unlike anything on Earth. Some volcanoes rise higher than Mount Everest, while others form broad, gently sloping domes spread across hundreds of kilometers. Recent observations suggest that Venus may indeed still be erupting. Subtle changes in atmospheric chemistry and surface features hint at ongoing volcanic activity. On Venus, lava behaves differently due to high surface temperatures and pressure. The planet's lack of plate tectonics means that heat may build up beneath the surface until it is released in massive planet-wide resurfacing events. In this way, Venusian volcanism may operate in cycles far more dramatic than Earth's steady tectonic churn. Mars offers another chapter in the story of extraterrestrial volcanoes. Home to the largest volcano in the solar system, Mars showcases the extremes that can arise on a smaller world. Olympus Mons towers nearly 3 times higher than Mount Everest, and spans an area roughly the size of a small country. Its sheer scale is possible because Mars has low gravity and no plate tectonics. On Earth, moving plates carry volcanoes away from their magma sources, limiting their size. On Mars, a volcano can sit over a hotspot for millions of years, growing larger with each eruption. Although Mars appears volcanically dormant today, evidence suggests that eruptions may have occurred relatively recently in geological terms. Some lava flows look fresh, with few impact craters, indicating they may be only a few million years old. If Mars retains pockets of internal heat, future eruptions are not impossible. Understanding Martian volcanism is crucial, as volcanic activity influences atmospheric evolution, climate, and the potential habitability of the planet. Beyond the inner rocky planets, volcanism takes on even more exotic forms among the moons of the outer solar system. Here, tidal forces play a dominant role. As moons orbit massive planets like Jupiter and Saturn, gravitational interactions stretch and squeeze them, generating heat through friction. This tidal heating can power intense volcanic activity, even in small, icy worlds far from the Sun. Io, a moon of Jupiter, stands as the most volcanically active body in the solar system. Its surface is a constantly changing mosaic of lava flows, sulfur deposits, and volcanic plumes. Hundreds of active volcanoes dot Io's surface, some erupting lava hotter than any found on Earth. These eruptions can launch material hundreds of kilometers into space, creating colorful plumes visible from orbit. Io's volcanism is driven almost entirely by tidal heating. As it orbits Jupiter, Io is pulled and twisted by the immense gravity of the gas giant and its neighboring moons. This relentless flexing generates enormous internal heat, keeping Io's interior partially molten. Unlike Earth, where water plays a key role in volcanic processes, Io's volcanoes involve molten rock and sulfur compounds, creating landscapes that look alien even to experienced planetary scientists. Europa, another moon of Jupiter, offers a different volcanic story. Its surface is a shell of ice, crisscrossed by cracks and ridges. Beneath that icy crust lies a vast subsurface ocean of liquid water. Europa's volcanism is not fiery in the traditional sense. Instead, it may involve cryovolcanism, where water, slush, or other volatiles erupt instead of molten rock. These icy eruptions can resurface the moon, transport material from the ocean below to the surface, and potentially create environments where life could exist. Cryovolcanism challenges our Earth-centered definition of volcanoes. On icy worlds, the magma may be water mixed with salts, ammonia, or methane. When internal heat builds up, this mixture can erupt through the surface, freezing instantly in the cold vacuum of space. Such processes blur the line between geology and hydrology, showing that volcanism is a universal expression of energy release, regardless of the materials involved. Enceladus, a small moon of Saturn, has become one of the most exciting targets in planetary science thanks to its active cryovolcanoes. From fractures near its south pole, Enceladus ejects towering plumes of water vapor, ice particles, and organic compounds into space. These geyser-like eruptions are powerful enough to feed Saturn's E-ring and reveal the presence of a global subsurface ocean. The discovery of Enceladus's plumes transformed our understanding of small moons. Despite its modest size, Enceladus remains geologically active due to tidal heating from Saturn. The interaction between internal heat, liquid water, and rocky material creates conditions that could be favorable for life. In this sense, volcanism becomes more than a geological curiosity. It becomes a potential driver of habitability beyond Earth. Titan, Saturn's largest moon, presents yet another variation on volcanic activity. With a thick atmosphere and lakes of liquid methane and ethane on its surface, Titan resembles a strange hybrid of Earth and an alien world. Evidence suggests that Titan may host cryovolcanoes that erupt mixtures of water and ammonia. These eruptions could resupply methane to the atmosphere, helping to maintain Titan's unique climate over long periods. Even distant dwarf planets show signs of volcanic processes. Pluto, once thought to be a frozen, inert world, surprised scientists with evidence of possible cryovolcanic features. Vast plains of nitrogen ice, towering icy mountains, and unusual dome-like structures hint at internal activity. While Pluto's volcanism is likely slow and subtle, it demonstrates that even the coldest corners of the solar system can remain dynamic. What unites all these diverse volcanic worlds is the fundamental role of internal energy. Whether powered by radioactive decay, residual heat from formation, or tidal forces, volcanism serves as a window into the hidden interiors of planets and moons. By studying volcanic features, scientists can infer composition, temperature, and internal structure, even when direct measurements are impossible. Volcanoes also play a critical role in shaping atmospheres. On Earth, volcanic eruptions release gases like water vapor, carbon dioxide, and sulfur dioxide, influencing climate and enabling long-term habitability. On other worlds, volcanism can create or replenish atmospheres, drive chemical reactions, and alter surface conditions. The thick atmosphere of Venus, the tenuous gases of Io, and the methane-rich skies of Titan all bear the fingerprints of volcanic processes. In the search for life beyond Earth, volcanoes take on added importance. Volcanic environments on Earth are often rich in chemical energy and host diverse ecosystems, even in extreme conditions. Hydrothermal vents on the ocean floor support life without sunlight, relying instead on chemical reactions fueled by Earth's internal heat. Similar environments may exist on icy moons with subsurface oceans, where volcanic or hydrothermal activity could provide energy and nutrients for life. Future missions will continue to explore volcanic worlds across the solar system. Orbiters, landers, and possibly even sample return missions will study lava flows, plume compositions, and thermal activity in unprecedented detail. Each new discovery will refine our understanding of how volcanoes operate under different conditions and what they reveal about planetary evolution. As we expand our view beyond Earth, volcanoes remind us that the solar system is not a static collection of rocks and ice, but a dynamic system filled with energy and change. Fire in its many forms burns throughout the solar system, from molten rock to erupting ice. These volcanic processes connect worlds separated by vast distances, revealing common physical principles expressed in endlessly creative ways. In the end, solar system volcanoes tell a story of continuity and diversity. They show that Earth is part of a broader family of active worlds, each shaped by its own balance of heat, gravity, and composition. By studying fire beyond Earth, we not only learn about distant planets and moons, but also gain a deeper appreciation for our own world and the forces that have shaped it over billions of years. Volcanic activity also plays a profound role in determining how long a world remains geologically alive. Small bodies lose heat quickly, while larger ones can stay active for billions of years. However, size alone does not tell the full story. Io is smaller than Earth's moon, yet it is far more active. Enceladus is tiny compared to Mars, yet it erupts continuously. These examples show that energy sources such as tidal heating can keep a world volcanically alive long after it should have frozen solid. Volcanoes therefore act as clocks, revealing whether a planet or moon is still evolving or has settled into geological silence. One of the most fascinating aspects of extraterrestrial volcanism is how lava itself behaves differently under alien conditions. On Earth, lava flows are influenced by gravity, atmospheric pressure, and chemical composition. On the moon, lava flowed farther and thinner because of low gravity and the absence of an atmosphere. On Mars, lava could pile up into massive shield volcanoes. On Io, lava temperatures may exceed 1,600 degrees Celsius, creating flows so fluid they behave almost like water. Each environment reshapes molten rock into new forms, reminding us that the same basic materials can produce radically different landscapes. Volcanic landscapes also preserve the history of planetary surfaces. Craters tell one story, but lava flows can erase that record, creating geological resets. Venus may have undergone global resurfacing events, where vast volcanic outpourings covered most of the planet within a relatively short time. If so, Venus's surface may be far younger than Earth's, despite the planet itself being just as old. Mars, by contrast, shows a surface where ancient volcanic plains coexist with younger lava flows, offering a layered record of its decline from an active world to a quieter one. Beyond shaping surfaces, volcanoes influence planetary interiors in ways that are still being unraveled. When magma rises and erupts, it redistributes heat and material. Over time, this can change how a planet cools, how its core behaves, and even whether it can sustain a magnetic field. Earth's magnetic field, which protects life from harmful radiation, is indirectly linked to internal heat and geological activity. Understanding volcanism elsewhere helps scientists explore why some planets have magnetic shields while others do not. The connection between volcanism and water is especially important. On Earth, volcanic gases likely helped create the early atmosphere and oceans. Water lowers the melting point of rock, making volcanism easier and more varied. On icy moons, water itself becomes the erupting material. This intimate relationship between volcanism and water suggests that volcanic worlds may be among the best places to search for life, not because they are gentle, but because they are energetic and chemically rich. Even extinct volcanoes have stories to tell. On Mercury, Mars, and the Moon, long dead volcanoes act as fossils of internal processes that no longer operate. By dating lava flows and analyzing their composition, scientists can reconstruct how these worlds cooled, differentiated, and changed over time. Each volcanic province is a chapter in a planetary autobiography written in stone. Looking farther outward, the concept of volcanism continues to evolve. Some scientists suggest that gas giants themselves may host forms of deep atmospheric volcanism, where material rises from the depths and erupts into upper layers of clouds. While not volcanoes in the traditional sense, these processes are driven by the same fundamental principle: internal energy seeking release. Even the sun, with its explosive flares and eruptions, can be seen as part of this broader cosmic pattern. Human exploration has only just begun to scratch the surface of these volcanic worlds. Robotic missions have flown through plumes, mapped lava flows, and detected thermal hotspots. Future missions may land near active vents, drill through ice shells, or even return samples from volcanic regions. Each step brings us closer to understanding how common volcanic activity is in planetary systems and what it means for the emergence of complex environments. Volcanoes also challenge our perception of danger and beauty. On Earth, they are both creators and destroyers. They bury cities, but they also create fertile soil and new land. On other worlds, volcanoes are not threats to human life, but they are keys to understanding planetary power. Images of glowing lava lakes on Io or towering geysers on Enceladus inspire awe and curiosity, expanding our sense of what nature can do. As science advances, volcanoes are increasingly seen not as isolated features, but as part of interconnected planetary systems. Volcanism interacts with atmospheres, oceans, ice shells, magnetic fields, and even orbital dynamics. A change in one component can ripple through the entire system. Studying volcanoes beyond Earth therefore helps scientists build a more holistic view of how planets function as integrated wholes. In a broader cosmic context, solar system volcanoes offer clues about worlds beyond our neighborhood. Thousands of exoplanets have been discovered orbiting distant stars, many of them rocky, many subjected to intense tidal forces. Some of these worlds may host volcanic activity far exceeding anything in our solar system. By understanding the volcanoes we can observe up close, scientists gain tools to interpret distant signals, such as atmospheric gases that may be produced by eruptions on faraway planets. Ultimately, the story of solar system volcanoes is a story of transformation. Fire reshapes rock, ice reshapes water, and energy reshapes worlds. From the quiet lava plains of the Moon to the violent eruptions of Io, from hidden oceans warmed by tidal heat to ancient volcanoes frozen in time, these processes reveal a universe that is active, creative, and endlessly diverse. Fire beyond Earth is not just about destruction or spectacle. It is about renewal, evolution, and possibility. Volcanoes remind us that planets are not static spheres drifting through space, but dynamic bodies with histories, cycles, and futures. By studying their eruptions, we learn how worlds are born, how they change, and how some may even become homes for life. In this sense, every volcano in the solar system is a message from beneath the surface, a signal that something is happening inside. Together, they form a grand narrative that stretches from the fiery youth of planets to the quiet aging of worlds long cool. And as long as there is internal heat, gravity, and motion, the story of volcanoes will continue, burning across the solar system and beyond. Another dimension of solar system volcanism lies in how eruptions evolve over time. On Earth, volcanoes can change personality, shifting from gentle lava flows to violent explosions depending on gas content and magma composition. Similar transitions may occur on other worlds, but in unfamiliar ways. On Io, repeated eruptions can rebuild entire regions within decades, erasing older landscapes almost as quickly as they form. On Venus, a long period of quiescence may end suddenly with enormous outpourings of lava, transforming the surface on a planetary scale. These rhythms of activity suggest that volcanism is not merely an isolated event, but a long-term process that reflects a world's internal balance. The chemistry of volcanic materials beyond Earth adds another layer of fascination. Earth's volcanoes mainly erupt silicate rocks rich in oxygen and silicon. On Io, sulfur and sulfur dioxide dominate, painting the surface in vivid yellows, reds, and blacks. On Titan, potential cryovolcanic eruptions may involve water-ammonia mixtures, acting like antifreeze and remaining liquid at lower temperatures. On Pluto, nitrogen and methane ices appear to behave like geological fluids. Each chemistry tells a story about a world's formation, temperature, and internal structure, turning volcanoes into chemical messengers from deep within alien interiors. Volcanoes also influence erosion and surface renewal in ways that differ dramatically from Earth. Wind and water shape Earth's landscapes over millions of years, but on airless bodies like the Moon and Mercury, volcanic features remain largely unchanged for billions of years. On Mars, thin air and occasional dust storms slowly modify volcanic terrains, while ancient lava flows remain visible from orbit. On icy moons, resurfacing through cryovolcanism can erase impact craters, making the surface appear young even if the body itself is ancient. This interplay between eruption and erosion helps scientists estimate surface ages and reconstruct geological timelines. The presence or absence of volcanoes can even determine whether a world appears alive or dead to distant observers. A volcanically active planet releases gases that can be detected from afar, altering atmospheric composition in measurable ways. In the future, astronomers studying exoplanet atmospheres may infer volcanic activity by detecting gases like sulfur compounds or carbon dioxide in unusual concentrations. In this way, lessons learned from solar system volcanoes will shape how humanity interprets worlds light years away. Volcanism also intersects with planetary hazards and human exploration. While active volcanoes pose risks on Earth, they also provide resources such as geothermal energy and mineral deposits. On other worlds, volcanoes may concentrate valuable materials or create environments suitable for future exploration. Lava tubes on the Moon and Mars, formed by ancient eruptions, could offer natural shelters for astronauts, protecting them from radiation and extreme temperatures. Thus, volcanic landscapes may one day support human presence beyond Earth. The emotional impact of volcanoes should not be overlooked. Throughout human history, volcanoes have inspired fear, reverence, and wonder. Seeing similar forces at work on distant worlds evokes a profound sense of connection between Earth and the cosmos. Images of glowing lava lakes on Io or towering icy plumes on Enceladus resonate deeply because they reveal familiar processes in unfamiliar settings. They remind us that the laws of physics apply everywhere, yet their outcomes are endlessly varied. Scientific debates continue about the limits of volcanism. How small can a body be and still sustain eruptions? How cold can a world become before activity ceases entirely? Discoveries like Enceladus and Pluto have already pushed those boundaries outward. Each new mission carries the potential to overturn assumptions, revealing activity where none was expected. This ongoing uncertainty is not a weakness of science, but its strength, driving exploration forward. As technology advances, scientists are developing new ways to study volcanic worlds. Thermal imaging reveals hidden hotspots. Spectroscopy identifies gases released by eruptions. Gravity measurements hint at molten layers beneath the surface. Combined, these tools allow researchers to study volcanoes remotely, transforming distant points of light into complex, dynamic worlds. The solar system becomes not just a collection of objects, but a network of interacting systems shaped by internal fire. Volcanoes also provide insight into planetary beginnings. Early in solar system history, intense volcanism was common as planets and moons cooled from their formation. These early eruptions released gases that formed atmospheres and oceans, setting the stage for later evolution. By studying ancient volcanic terrains, scientists glimpsed conditions that may resemble those on young exoplanets still forming today. In this way, ancient lava flows become time machines, connecting past, present, and future. Even silence has meaning in the study of volcanoes. Worlds where volcanism has ceased entirely offer clues about heat loss, composition, and structural rigidity. Comparing active and inactive bodies helps scientists understand thresholds and tipping points. Why did Mars largely shut down while Earth remained active? Why did the Moon cool so quickly? These questions lead back to volcanoes, which serve as visible indicators of invisible processes. In the grand narrative of planetary science, volcanoes are storytellers. They speak of heat and motion, of stress and release, of creation and decay. They reveal that no world is truly static, even if change unfolds slowly. Fire beyond Earth is not always bright or violent. Sometimes it is subtle, hidden beneath ice or rock, reshaping worlds over eons. As exploration continues, the catalog of volcanic worlds will likely expand. New moons may be found with active interiors. New forms of volcanism may be discovered that challenge existing definitions. Each revelation will deepen our understanding of how common and how diverse planetary activity truly is. The study of solar system volcanoes ultimately reshapes how humanity views its place in the universe. Earth's volcanoes are no longer unique curiosities, but part of a broader cosmic pattern. Fire is not confined to our planet. It is a universal force that sculpts worlds wherever conditions allow. By following the traces of lava and ice across space, we learn that Earth is both special and connected, one expression of a much larger, dynamic cosmos. In this continuing story, volcanoes remain symbols of energy, transformation, and possibility. They remind us that beneath every surface lies a hidden interior, and that even in the cold darkness of space, worlds can burn from within. Volcanoes also act as bridges between a planet's deep interior and its surface environment. Without volcanism, the materials locked inside a world would remain hidden forever. Every eruption is a delivery system, carrying information from deep below upward into sunlight and space. The minerals found in lava flows, the gases released into an atmosphere, and the heat patterns detected from orbit all tell scientists what lies beneath the crust. In this way, volcanoes function like natural probes, allowing humanity to study planetary interiors without drilling a single hole. On Earth, volcanic gases played a crucial role in shaping the early environment. Water vapor released from countless eruptions condensed to form oceans. Carbon dioxide helped regulate temperature, while nitrogen built the foundation of the atmosphere. Similar processes likely occurred on other planets. Early Mars may have relied on volcanism to thicken its atmosphere and warm its surface, making liquid water possible. When volcanic activity declined, Mars gradually lost its atmosphere and transformed into the cold desert world we see today. The rise and fall of volcanism may therefore mark the difference between a habitable world and a barren one. The timing of volcanic activity is just as important as its intensity. A planet that erupts too violently or too frequently may struggle to maintain stable conditions, while a planet that cools too quickly may lose its atmosphere and water. Earth appears to occupy a narrow middle ground, where volcanism is steady enough to recycle materials and regulate climate, but not so extreme that it sterilizes the surface. Studying other worlds allows scientists to understand how rare or common this balance might be across the universe. Volcanoes also reshape planetary surfaces in ways that influence future geological activity. Lava flows can bury faults, seal fractures, or create new pathways for magma to rise. Over time, this feedback loop determines where future eruptions occur. On Mars, massive volcanic provinces like Tharsis may have altered the planet's rotation slightly by redistributing enormous amounts of mass. Such changes could have influenced climate, atmospheric circulation, and even the stability of water on the surface. Volcanoes, therefore, are not passive features. They actively participate in the evolution of entire planets. On icy moons, Cryovolcanism may serve an equally transformative role. By cycling material between the interior ocean and the surface, icy eruptions prevent these worlds from becoming geologically stagnant. Fresh ice deposits reflect sunlight, influencing surface temperatures, while subsurface exchanges may keep oceans chemically balanced. In the case of Europa and Enceladus, cryovolcanism could be essential for maintaining environments where life might persist over long periods. The concept of volcanic heat-driving ecosystems is not limited to Earth. Deep beneath Earth's oceans, hydrothermal vents host thriving communities of organisms that rely on chemical energy rather than sunlight. These ecosystems demonstrate that life does not require gentle conditions, only a reliable source of energy and chemistry. On icy moons with subsurface oceans, volcanic or hydrothermal activity at the seafloor could provide similar conditions. If life exists beyond Earth, it may be found not on sunny surfaces, but in dark volcanic depths. Volcanoes also influence how planets age. Young worlds tend to be hotter and more volcanically active, with frequent eruptions reshaping their surfaces. As time passes, internal heat dissipates, eruptions become less common and surfaces stabilize. By comparing volcanic features across the solar system, scientists can place worlds along this evolutionary timeline. Mercury and the Moon represent worlds that cooled quickly. Earth and Venus remain active. Mars sits somewhere in between, preserving evidence of both youth and decline. Venus remains a particularly important puzzle. Despite its similarities to Earth, its surface conditions are hostile, and its atmosphere is thick and scorching. If Venus is still volcanically active, those eruptions may be feeding its runaway greenhouse effect. Understanding Venusian volcanism could therefore help scientists answer one of the most important questions in planetary science: how two nearly identical planets can evolve into radically different worlds. This knowledge has direct implications for interpreting Earth-sized exoplanets orbiting distant stars. Volcanoes can also act as markers of internal structure. The distribution of volcanic features reveals where a planet's crust is thin or thick, where heat concentrates, and how magma moves. On Mars, chains of volcanoes suggest long-lived hotspots beneath a stationary crust. On Io, volcanoes cluster where tidal stresses are strongest. On Earth, volcanic arcs trace the boundaries of tectonic plates. Each pattern reflects a different internal architecture, making volcanism a diagnostic tool for planetary anatomy. As exploration continues, scientists are becoming increasingly interested in monitoring active volcanoes beyond Earth in real time. Detecting changes in thermal emissions, plume activity, or surface composition allows researchers to watch geological processes unfold. These observations transform volcanoes from static landmarks into dynamic systems. Watching a volcano erupt on another world is like witnessing a chapter of planetary history being written in the present tense. Volcanoes also affect how planets interact with space. Eruptions can inject particles into surrounding space environments, influencing magnetospheres and radiation belts. Io's volcanic output feeds Jupiter's magnetosphere, creating intense radiation that affects nearby moons and spacecraft. Enceladus's plumes contribute material to Saturn's rings. These interactions show that volcanism does not stop at the surface. It extends outward, shaping entire planetary systems. The diversity of volcanic forms challenges any single definition of what a volcano is. On Earth, a volcano is typically imagined as a mountain that erupts lava and ash. In the broader solar system, volcanoes can be cracks in ice, vast lava plains, underground vents, or geysers shooting material into space. This diversity forces scientists to think in terms of processes rather than appearances. At its core, volcanism is about energy transfer, regardless of whether the material is rock, ice, or gas. Volcanoes also serve as reminders that planetary science is an evolving field. Many of the most exciting discoveries about extraterrestrial volcanism have occurred in just the past few decades. Before space exploration, volcanoes were thought to be mostly an earthly phenomenon. Now they are recognized as fundamental features of planetary bodies throughout the solar system. Each new mission has expanded the known range of volcanic activity, revealing worlds that defy expectations. In the future, volcanism may play a role in how humanity expands into space. Understanding volcanic hazards will be essential for long-term exploration and settlement. At the same time, volcanic regions may offer resources such as heat, shelter, and raw materials. Lava tubes could provide ready-made habitats, while geothermal energy could support sustained human presence. What was once seen as a destructive force may become a valuable ally. Volcanoes also influence how we emotionally connect with other worlds. Images of flowing lava or erupting plumes create a sense of immediacy and vitality. They make distant planets feel less like abstract objects and more like places with ongoing stories. This emotional connection fuels public interest, inspires future scientists, and reinforces the idea that exploration is not just about knowledge, but about wonder. As scientists continue to map volcanic features across the solar system, patterns emerge that hint at universal principles. Heat flows from hot interiors to cold surfaces. Gravity shapes how materials move. Chemistry determines what erupts and how it behaves. These principles apply everywhere, yet their outcomes are shaped by local conditions. Volcanoes therefore embody both the unity and diversity of the cosmos. The study of solar system volcanoes ultimately deepens our understanding of Earth itself. By seeing how volcanism operates under different conditions, scientists gain perspective on why Earth works the way it does. Earth's balance of heat, water, and tectonics appears increasingly precious when compared to worlds that are too hot, too cold, or too unstable. Volcanoes, once feared as symbols of destruction, become indicators of planetary vitality. Fire beyond Earth is not a metaphor, but a reality expressed in many forms. Molten rock, erupting ice, and energetic gases all represent the same underlying truth. Planets and moons are active participants in cosmic evolution. They are shaped from within, driven by forces that operate over immense spans of time. In the vastness of space, volcanoes reveal that change is universal. No world remains exactly as it began. Through eruptions, great and small, surfaces are renewed, atmospheres are shaped, and possibilities are created. Solar system volcanoes show us that even in darkness and cold, energy persists, reshaping worlds from the inside out. And as long as there are planets with internal heat, gravitational forces, and chemical complexity, the story of volcanism will continue. Fire will rise, ice will fracture, and worlds will speak through their eruptions. In listening to those signals, humanity learns not only about distant places, but about the dynamic nature of the universe itself. Volcanoes also act as long-term stabilizers and destabilizers of planetary environments. On Earth, the slow release of carbon dioxide through volcanic activity is balanced by weathering processes that lock carbon away in rocks, helping regulate global temperatures over millions of years. This delicate balance may not exist on other worlds. On Venus, volcanic gases may accumulate in the atmosphere without an efficient removal mechanism, contributing to extreme greenhouse conditions. On Mars, declining volcanism may have removed a crucial source of atmospheric replenishment, accelerating atmospheric loss to space. These contrasting outcomes show that volcanism alone does not guarantee habitability, but its interaction with other planetary systems can determine a world's fate. Volcanic activity can also influence planetary rotation and orientation in subtle but meaningful ways. Massive volcanic provinces redistribute enormous amounts of mass across a planet's surface. Over geological time, this redistribution can alter a planet's spin axis through a process known as true polar wander. Some scientists suggest that the immense volcanic bulge on Mars may have shifted the planet's orientation, affecting climate patterns and the stability of surface water. In this sense, volcanoes do not merely reshape landscapes. They can reshape the entire framework in which climates operate. The relationship between volcanism and impact events is another area of active research. Large asteroid impacts can fracture planetary crusts, creating pathways for magma to rise. On the Moon and Mercury, some volcanic plains appear to have formed after massive impacts, suggesting that collisions may have triggered eruptions. Conversely, extensive volcanic resurfacing can erase evidence of past impacts, complicating efforts to reconstruct early solar system history. Volcanoes and impacts together form a dynamic interplay between internal and external forces, shaping planetary surfaces through both violence and renewal. Volcanoes also influence the way light and heat are reflected and absorbed by planetary surfaces. Fresh lava flows are often dark, absorbing more sunlight and warming the surrounding region. On icy worlds, cryovolcanic deposits may be brighter, reflecting sunlight and cooling the surface. These changes in surface reflectivity can create feedback loops that affect local and even global temperatures. Over long periods, such feedbacks can influence atmospheric circulation and climate stability. In the context of planetary exploration, volcanoes present both challenges and opportunities. Active eruptions pose risks to spacecraft, but they also offer rare chances to sample interior material without drilling. Flying through plumes, as missions have done at Enceladus, allows scientists to analyze subsurface chemistry directly. Future missions may attempt similar approaches at Europa or even Io, despite the harsh radiation environment. Each encounter brings new data that refine models of planetary interiors and thermal evolution. Volcanism also raises philosophical questions about what it means for a world to be alive. While planets are not living organisms, active geology gives them lifelike qualities. They grow, change, and recycle material. A volcanically active world appears dynamic and responsive, while a geologically dead one feels static and frozen in time. This perception influences how humans emotionally categorize worlds, often associating activity with potential and stillness with decline. As scientists push the boundaries of observation, they are beginning to model how volcanic activity might appear on worlds far different from those in our solar system. Super-Earths with stronger gravity may host thicker crusts and more pressurized magma systems. Lava on such worlds could erupt explosively or remain trapped deep below the surface. Tidally locked exoplanets orbiting close to their stars may experience extreme volcanic activity on their star-facing sides. By understanding solar system volcanoes, researchers build the foundation needed to imagine these distant possibilities. Volcanoes also serve as reminders of deep time. A single eruption may last days or years, but volcanic provinces record histories spanning billions of years. Layer upon layer of lava preserves a timeline of internal processes, each flow marking a moment in a planet's evolving story. When scientists read these layers, they reconstruct sequences of events that shaped entire worlds long before humans existed. The cultural impact of volcanoes extends beyond science. Images of alien eruptions inspire art, literature, and imagination. They challenge creators to envision landscapes shaped by unfamiliar forces, expanding the boundaries of science fiction and speculative thought. These creative responses, in turn, influence how society perceives space exploration, reinforcing the idea that other worlds are not empty rocks, but places of drama and transformation. Volcanoes also highlight the importance of comparative planetology. No single world can explain volcanism in all its forms. Only by comparing Earth with Mars, Venus, Io, and icy moons can scientists identify patterns and exceptions. This comparative approach transforms volcanoes into a unifying theme, connecting diverse worlds through shared physical principles while celebrating their differences. As research continues, some long-held assumptions are being challenged. It was once believed that small bodies could not remain volcanically active for long periods. Discoveries like Enceladus have overturned that view. Similarly, the idea that icy worlds are inert has been replaced by a recognition of their dynamic interiors. These shifts demonstrate how volcanism remains at the forefront of planetary discovery, continually reshaping scientific understanding. In practical terms, volcanoes may one day help guide the selection of exploration targets. Worlds with active volcanism offer fresh material, chemical energy, and geological diversity. They may also be more likely to host environments suitable for life or future human activity. Identifying and prioritizing such worlds will be a key task for future space agencies and missions. The study of solar system volcanoes ultimately reinforces a profound truth. Energy drives complexity. Where there is heat and motion, there is change. Volcanoes are visible expressions of that energy, making the invisible visible. They turn internal processes into surface features that can be observed, measured, and understood. Fire beyond Earth is not uniform or predictable. It appears as molten rock, erupting ice, sulfurous plumes, and subtle thermal anomalies. Each manifestation tells a different story, shaped by local conditions and cosmic history. Together, these stories form a tapestry that reveals the dynamic nature of planetary bodies across the solar system. As humanity looks outward, volcanoes remind us that exploration is as much about understanding processes as it is about discovering places. Each volcanic world teaches lessons that apply beyond its own boundaries, informing models of planet formation, evolution, and potential habitability. In the end, solar system volcanoes stand as symbols of persistence. Long after surfaces cool and atmospheres thin, internal heat can endure, finding ways to escape and reshape the world above. These eruptions, whether violent or gentle, speak of worlds that refuse to be static. Fire beyond Earth continues to burn, not as a single flame, but as countless expressions of planetary energy. By studying these distant fires, humanity gains insight into the forces that shaped our own world and continues to shape countless others across the universe.